Hello everyone, my name is Tom and I'm going to present to you our work on unknown mixing times in apprenticeship and reinforcement learning. This is a joint work with Alon, Cohen, Haim, Kaplan and Yishay Mansour that we did at Google AI. In short, we analyzed reinforcement learning algorithms in the average reward criteria. We revisit a technique for Markov chain theory called coupling from the past. This is a technique for getting a perfect sample from the stationary distribution of a Markov chain. Using CFTP, we derive reinforcement learning algorithms for the average reward criteria that do not need to know the mixing time. Let's first start with some notation. Given an MDP M that is composed of a state space, an action space, a reward signal, and transition kernels, given a policy pi, this MDP is reduced to a Markov reward process, M pi, given by a state space, a transition matrix, and a reward signal. If the MDP is ergodic, then each policy pi is associated with a stationary distribution mu, which is a left eigenvector of the transition matrix P pi. The average reward is defined by rho pi, and it's the reward under the stationary distribution mu. The optimal policy in the MDP-M for the average reward criteria is the policy that maximizes the average reward. Now let's look what is the mixing time. We define by P pi t at x0 the distribution over states when following policy pi from state x0 for t steps. The mixing time is the smallest t such that this distribution is close to the stationary distribution under the total variation distance. And the total variation distance is a distance between two distributions measured by the L1 norm. Now, intuitively, if we wait t mix steps, we get a sample from the stationary distribution that is almost distributed like it. What can we do when we don't know the mixing time? So, first of all, many RL algorithms assume that we know the mixing time or an upper bound for any policy. But when it's unknown, we can either estimate the MDP transition matrices and compute the stationary distribution for each policy. This approximation is not tight and it's also biased. The second thing that we can do is to estimate the mixing time from samples for each policy. But this process is less sample efficient. In this work, we focus on getting unbiased samples from the stationary distribution with a known mixing time. We do this using a technique that is called coupling from the past. Let's see how it works. We start as simulations, basically a simulation from each state, and at each iteration we sample the next state from the transition dynamics of the Markov chain. We start this simulation at -infinity, and when two simulations coalesce together, they continue as one simulation. We wait at time t equals 0, and then we get a perfect sample from the stationary distribution. Now, it's important to note that we must run the simulation backwards, meaning that we start at time 0 and we simulate increasing suffixes and we always measure the stationary distribution at time t equals 0. Otherwise, the sample is biased, and there are more details in the paper about it. What do we know about the coalescence time? So first of all, it's bounded in expectation by the mixing time. We can also get a high probability bound, and the proofs for that were derived by Popp and Wilson in the original paper. In our paper, we provide an alternative proof which we believe is more accessible. Let's see an example. Here we have a simple Markov chain with two states and reward only in one state. We start from some initial distribution mu0, and the stationary distribution is 2/3 of being in the left state and 1/3 for being in the right state. We can compute analytically the mixing time and the coalescence time for this chain, and specifically in this chain, the coalescence time is actually shorter than the mixing time. Now we can check what happens when we try to guess the mixing time. So first of all, we can see in this right curve here that if we underestimate the mixing time, we get biased samples from the stationary distributions and therefore a biased sample estimation of the stationary reward. If we do the Prop-Wilson thing, then we get unbiased estimates, and that's why the MSE is decreasing to 0. And if we overestimate, we also get an unbiased estimate, but it's less sample efficient. How can we use CFTP in reinforcement learning? In the paper, we show 3 examples. One is the policy gradient algorithm. The second is the apprenticeship learning algorithm. And the third one is a dynamic data structure that allows us to evaluate the average reward of any policy in MDP. For policy gradient, let's recall how is it defined in the average reward case. So the policy gradient is defined by expectation over state sampled from the stationary distribution and the actions that are sampled from the policy for which we take the gradient for, where for each state action we take the gradient of the log probability of the policy times the Q function of this policy at this state. The Q function is defined by the expected reward that we get if we start at state S0, take action A and follow pi after that, minus the average reward of that policy. How can we use CFTP to get an estimate of this gradient? So what we do is that we start the simulation by sampling a state using the CFTP. So we get a state that is distributed according to the stationary state distribution. Let's call it S2. Then we take one action by following policy pi, and the other action is the actions that we want to estimate the gradient for. We wait till these 2 trajectories coalesce, and when they coalesce, we measure the difference in reward the 2 trajectories collected up to this point. And this makes an unbiased estimate of the policy gradient. For apprenticeship learning, let's remember what is the formulation. So we have a reward that is linear in some features. We can define the expected features for policy pi under the stationary distribution. And then the average reward is linear in these expected features. There's an expert that provides demonstrations, and we get an estimate of the expected features of the expert policy. And the goal is to find a policy pi with average reward that is close to that of the expert for any reward coefficients W. Basically solving this max-min optimization problem. The general idea for the solution is that there is a reward player that plays a no-regret algorithm. Specifically, we refer to the multiplicative weights or hedge algorithm in that case. And there is a policy player that plays the optimal policy with respect to the current reward. To estimate the gradient of the reward player, we need an unbiased estimate of the difference of the feature expectations. We can use CFTP to get this estimate. How do we do that? We sample, in the paper, we analyze the sample and time complexity bounds for apprenticeship learning with average reward. The result is based on martingale concentration bounds for unbounded variables, and it works with unknown mixing times. Thank you for listening, and if you have more questions, please reach out. Thanks.